this is a big combination of classical mechanics, optics, and quantum mechanics. We've already gotten a little bit into this, and we need to look in detail on how an oscillator, a double-dimensional oscillator, is related to Schrödinger-like equations. And then we're going to go carefully into another way to take care of eigenfunctions in this for this particular type of Hamiltonian or Lagrangian. And we're going to be generalizing today the complex variables. That is, functions of complex variable were a great discovery in mathematics, but they bothered people like Hamilton because it only took care of x and y, and they thought such a wonderful piece of mathematics ought to be able to take care of x, y, and z. So Hamiltonian looked and looked and looked and just couldn't find any sort of decent mathematical thing to take care of three variables. And then one day he's walking across the bridge in Dublin, and it suddenly occurs to him, why not 2 plus 2 makes 4? With 4 things I could make a generalization of complex numbers. Well, that grew into what we call spinors, and that's what we're going to talk about today, but we'll also talk about Hamilton in this context. We've had enough of him as far as equations of motion go, but today we'll see, I think, what is one of his greatest discoveries. And it's also going to help you in other classes, all sorts of physics, nuclear magnetic resonance. Eventually, I think it's going to help us with relativity. We'll get into that today. But the power of this, as you'll see in the second half of this class today, is really wonderful for visualization as well as computation. And normally we cover this in great detail in the course on group theory and quantum mechanics, but this part of it should be in a classical mechanics course, so it is. Now, just to review, we've already been through making equations of motions of these coupled oscillators of various variety, and looking at their eigensolutions, which are their normal modes. And when we did that, we noticed that the eigenvalue of the classical equation involving second derivatives of the coordinates, in this case x1 and x2, had an interpretation that was a little bit, well, different from what you would have in quantum mechanics, where energy is proportional to frequency. Here is the eigenvalues are proportional to the square of the eigenfrequency. That is going to change a little bit in the way we're going to attack the problem today. The thing that leads to use of Hamilton's quaternions or Pauli spinors involves a little twist in the development of this two-dimensional equation of motion to make it into a first-order differential equation. So that analogy, at first is an analogy, but isn't everything we do in science an analogy with something else? The two-state Schrödinger equation is just a Hermitian matrix multiplied by a two-dimensional vector. And the idea is that that gives an imaginary number times a partial derivative with respect to time. The self-conjugate matrix that the unitary theory of quantum mechanics requires demands that this thing, which is a generator of those unitary transformations, be self-conjugate, that is, Hermitian transpose, which means switch K and J, and then star it, conjugate it. If you do that and they come out equal, you're okay with standard quantum mechanics. If they don't, you've got something that can blow up, change its amplitude, And that's something that relativity would require. That's where relativity changes its amplitudes in a Lorentz transformation. Now, when we start off with a self-conjugate matrix, it has then only four components. If this was allowed to have complex numbers in all four spots, and there were no relationships like this one that makes this number here be essentially the same, just a conjugate of this number, and then it makes these two numbers be real, so that H11 star equals H11. So I call that A. Then B and C are the real and imaginary part of the next part of this matrix, and then I come over here and I have to use the same B and C, but with a change of sign here. And then I'm back to the diagonal again, and therefore I have to have a real number. So using this as a model for a classical system is what we're going to study. Now what's also interesting about this is that we will be using, as we have been for our oscillators, our coordinate x1 and x2. Now I'm calling them A1 and A2, which is amplitude 1 and amplitude 2 in a quantum mechanical setting. Later it becomes either destruction or creation operators, but let's forget about that for a moment, or for a fairly long time. I have here a complex number in both components for the state. Now the thing to notice, and this doesn't happen again, that is at higher dimensions, the number of parameters for the Hamiltonian here is 4, but it's all exactly equal to the number of parameters for the state, that is for the complex coordinates that are describing this oscillation. And that is something that makes us very special. In fact, I would say that this is the beginning of some kind of proof of why we have 4 dimensions of space and time. That seems crazy, but then Hamilton thought the whole business was pretty wonderfully crazy when he discovered the mathematics that we're going to be talking about. In any case, what we're going to do is we're going to take this equation of motion right here and separate the real and the imaginary parts of the amplitudes. Now we're calling them x1 plus ip1, that's the first amplitude, and x2 plus ip2, that's the second one, as though they were positions and momenta, which is perfectly reasonable to do if you're used to having phasor amplitudes. So little clocks that we've drawn so far for describing oscillation. We've got 2 of them going here, clock 1 and clock 2. And a clock that can get bigger and smaller and turn at various different rates is what quantum mechanics is all about. This is quantum mechanics of 2 states, so there are only 2 clocks. Now what we have to do is convert this equation right here into real first-order differential equations. So very few quantum mechanics books bother to do that. It's just assumed, oh, well, you use complex numbers, don't you? And you have an I here in Schrodinger's equation, don't you? And nobody really asks the questions, what are we doing with these complex numbers? Can't we do it real? Well, yes, you can make it real. We're going to have to do it to make connection with this, because this is, at least the way we've been doing it, totally real. So there's the equation of motion written out in the variables that we're actually going to use. The 4 things that drive the Hamiltonian, and then the 4 things that get driven by the Hamiltonian, the phasors that get have to obey this equation of motion for themselves. So basically what we're going to do is go ahead and take the first derivative of x1 p1 here, and that's little dots on top of the x1 and the p1 there indicate that I've done that. And then I have to go through here and take the a here and multiply it by x1, okay? And then I've got the p1 dot over here, okay? and I've got b minus ic times that. That gives me 4 terms that are right here. Actually, more than that. And then, let's see if there's anything else. But anyway, what I'm going to do is I'm simply going to separate the real part of this, make that an equation over here. Okay, and this is indicated by the green line. Okay, this connecting this. We're having trouble with something. I don't know why that does that, but it does it. More and more. Then the imaginary part, there's a bunch of things here that have eyes on them. That's the red part of this. That gives me this real equation right here. Okay. Then I do the same thing for the second component. So now I've got 4 real equations of motion. Well, let's see if we can relate that to that thing. It doesn't look like it right now, but what we're going to do is notice that if I start with a classical Hamiltonian, and then parentheses, designed to give what I want, but it's a fairly reasonable sort of thing. It's sort of a symmetrized version of this thing, but with some extra stuff in it. Okay? So this little h sub c is a classical equation of the 4 variables, xp 1 and 2, that will, if we are careful, give us Hamilton's equation of motion. This is a Hamiltonian. We're just treating it like one. X dot is partial h with respect to p for component 1 and 2, and then p dot is minus the partial derivative of this Hamiltonian with respect to x 1 and 2. Okay, so going through that's pretty easy to do. I put those variables in order there. x1, x2, and p2 show up on this one. x1, p1, p2, and x2 show up on this one. Then I see p1, p2, and x1 showing up there. x1, x2, and p1 showing up in the 4th equation. And they're the same. Okay? So here's what we get from quantum mechanics. Here's what we get with a contrived, I said, designed this to give the, but there isn't much choice here. This is about all I can do. Okay? So that's the deal. QM versus classical equations are identical for this 2-state system. Okay? Now people talk vaguely about how, yeah, this is oscillators, right? Well, we're being explicit. This apparently I have not seen written anywhere, but it should be. Okay? So then I do one more thing. I say, okay, well, I really want a second order equation up here, so let's just take a derivative of each one of these. Okay? Now, at this point, we're going to do 2 things to make it a little simpler, keep the algebra under control, so to speak. I'm going to assume, and I'm saying this in 2 places here, so I make sure you don't forget that that's part of the idealization here. I don't want anybody meddling in the middle of the motion with this Hamiltonian. I don't want that partial with respect to time to be anything but 0. Okay, so no meddling mid-course, all right? So for constant A, B, C, and D, what we're writing here is going to be true. Okay? So, what I'm getting here is an x dot dot, means I get an AP1 dot. No A dot is constant. So I get P dot 1, and so I go up here and get P1 dot and stick it in there. Okay? Same with this guy over here. I've got a P2 dot now after I took the double time derivative of this x1. Okay? I stick him in there. Okay? And so forth. I'm going to also be seeing a P2 dot that needs to be taken care of right there. Okay? So that's our equation of x dot dot is equal to, and now a linear combination of x1s and p1s showing up like that. And then I go over here and I'm going to do the second dimension, roughly the same sort of thing appearing. So I can turn this into a matrix equation that has a second derivative of the coordinates with everything real. Okay. Now, if we're going to do relativity and funny stuff, then A, B, C, and D may be complex. So that would be a different equation in that case. But for this one, certainly, and this is the other thing I did, I set the C thing here to 0. Now we're going to talk about that C. That C is really a key parameter for certain things. So with circular and chiral things that go around. And right now we're just talking about something that doesn't have that, so we're setting it equal to 0. We don't need it here. But you can see right away, I have here a double derivative of x1 and x2. That's x1 dot dot, x2 dot dot, okay, is equal to minus a K matrix. Exactly this K matrix that we talked about before, with K11 being this quadratic combination of the parameters that occur in the Hamiltonian, the A and the B in this case. And then the A, B, and D get into the act for the coupling that's right here, K12, and they're equal. So you don't have any inequality between this. This thing is very nicely symmetrized. And this then is different from this one. K11 is different from K22 if A and D are different. Okay, so far so good. All right, so here is a rather simple way to get the same result. Just look at the equation. It's partial with respect to t, okay, derivative with respect to t. When I say partial, this thing is in the wave equation. It's a simply a 2 by 2 matrix here. That operator is having the same effect as this operator, this matrix operator. Okay? So really what I should be saying here is forget the thing that we're acting on. Here's what's acting. I times partial respect to time, and then a matrix, A, B, B, D. Okay? Now, if that's true, then I take the square of this, get an I squared, which is a minus sign, and the square of a differential operator, which is a second derivative. Okay, and then I get this thing squared. Okay? That checks. There's A squared plus B squared. There's ABD. There it is again. And there's B squared plus D squared. Okay? Now that's just with C equals 0. It doesn't have to be 0. You see. There I can put the C back. And now I have an operator that's complex. But Hermitian. Okay? So, I can even play with this thing, and that's a good thing. The C is what makes the world go round, so to speak. Okay? It's the thing that makes current possible. Well, we're going to come and name these things in a funny kind of way. Okay, so what we're going to do now is we're going to say, okay, I can do both of these problems. Now let's go back and do it kind of in the way that all the people in quantum optics do now, except they don't use anything but the old Pauli naming. What we're going to do is we're going to say, okay, I've got a Hamiltonian like this Hermitian operator. It's got 4 parameters, A, B, C, and D, multiplying this matrix, then this matrix, then this matrix, then this matrix. Okay? Now, this is sort of a short circuit here for solving an oscillator equation. We already know that what you want to do, using our algebraic techniques, is find a spectral decomposition of this thing and then write that Hamiltonian in terms of the projection operators, right? Well, that's fine. That's a nice bookkeeping. That's something you can sort of count on. But what we're trying to get here is a better visualization. So these are going to be kind of our projection operators, except they don't quite look like projection operators. They're going to be Hamilton's quaternions or Pauli spinners. If I collect these two into an antisymmetric and a symmetric part, I leave these alone. Okay? Now, we've done this already when we were first starting this class with the bouncing balls, right? We worked with this one guy right here, and we worked with this guy, right? We never got around to using that one. And of course we have that one along for the ride all the time, right? We'll call that one sigma 0, okay? Or sigma 1. It's a unit operator, okay? But once I've got him out of the Hamiltonian, then I've got left here these three guys. Now the proper name, that is the jargony name, for this guy right here is sigma Z. Pauli, right? That's the guy that's up at the, let's see if where he's located. Yeah, right at the top of this column right here. His name that we call him is over here. We call him asymmetric diagonal because he's got a coefficient A and D. Easy to remember, maybe. Okay, that's what he is. He's asymmetric on the diagonal. He is diagonal, but perhaps doesn't have a symmetry of A equal to D. If he did, it would be a unit matrix times a constant. Okay? So that guy right there, with a 1/2 in, is called a spin operator. Okay? And it's Z. That's Pauli's third component. It's our first. Okay? Now the next one in line here is B for bilateral balanced. Now this is where the coupling is balanced and there isn't anything making our diagonal do anything. So this is my mnemonic. Okay? That one is Pauli's X operator. It's his first, our second. Okay? And then this last one, C, and there's lots of things that begin with C that describe this one. This is a big actor. Okay? As you'll see, it gives chiral motion, left and right-handed. Circular polarization. It's the only complex component here. It also gives you Coriolis motion for this two-dimensional oscillator, a Foucault-like pendulum motion. It describes cyclotron orbits. It's a magnetic field, makes things try to orbit. It's curly. And here's a real one. Whenever you have a two-state system, you need this one to get current going, to get something going between one side or other. Why is that? Because if, as we showed in our first one-dimensional oscillator situation, you're in phase, no energy going between you. Okay? Doesn't matter what the amplitude is. You see, it could be like this. Right? Doesn't matter. No energy. Phase space diagram, work diagram, zero area. Okay? And when you're out of phase, pi out of phase, that's the only two possibilities you have. You have real numbers, right? You either have plus and plus or plus minus. When you're out of phase, again, no, the area work from is zero area, no energy being transferred. So C is the one that makes, I could put currency here. Here's where your currency is, your payoff, right? You want to pay, you be ahead of phase. You want to get paid, you get behind. You see. Okay, so this is really fundamental, very fundamental a notion of how things move. Okay? Now, without turning the C on, which we won't do for a little bit here, I only have A and B and D to play with. Here's a kind of oscillator that we're going to have for asymmetry, just diagonal. That means that the major and minor axes of our potential ellipse, which we hope to have, or this thing isn't stable, is going to have maybe a slow axis on number 1 and a fast axis on number 2, or vice versa. But the main thing is the axes are not anything but what we used for our coordinates to start with. Then, anytime I put a difference between A and D, and I haven't turned the C on, remember, so B is just sitting there being balanced, but it isn't balanced this way, so your eigenvectors are going to be somewhere between x1 and x2 axes, maybe down here, up there, but they're normal modes, so they'll always be perpendicular to each other, so there'll be a slow and a fast axis with some rotation. Okay, now slow and fast means astigmatism, and then this is a rotation of the astigmatism. So when you go to the eye doctor, he's going to look to see how astigmatic you are, if at all, and then he's going to figure out what's the angle that that's at. And then he's going to write your prescription for a glass or contact lens that undoes that. Okay, that's a miracle of optics that lets me see there's even a class in here. Okay. Oh, you're gone now. Okay, now this one, B symmetry, is the one that splits the difference between x and y perfectly. It has a 45-degree angle for its eigenaxis. It could be the slow one or it could be the fast one. We've been showing it where this is the slow one on our thing. So these are the two main types of symmetry. Well, these are the two main types, and this is just in between there somewhere. We'll talk about it actually at the very end. We'll take care of A, B, and C fairly shortly here. Okay? Now, as I said, these things are known as Pauli-Spinner operators. Okay? Last one for Pauli is the first one for us. And then the first one for us is Pauli's, I'm sorry, the second one for us is Pauli's first, and then the C and the Y. His third is our second. And we have no disagreement about what to call that. We call it 0 or 1. Okay? Now this is 1927 that this comes up. Okay? And he's worried about magnetism of electrons. Okay? But Jordan, the mathematician, was already working on this. And I think Jordan was more honest. He realized that Hamilton had already gotten these things. They're called I, J, and K. Now it's just one in I. That's basically one real and one imaginary. Okay? But what he's noticing when he works out an algebra for these things, and he gets basically Pauli's algebra, you take an I factor and stick it on all of Pauli's matrices, the three main actors, forget about the unit, and they're the same. They've got the same rules as Hamilton. Okay? Why this isn't pointed out in every quantum mechanics book, I don't know. But it's definitely true. And the I, J, and K doesn't, well, where does it show up in your calculus? You use I, J, and K for your axes, right? That's Josiah Willard Gibbs, the American physicist who went over to, brush off the hayseeds and be part of the erudite European scientific culture, and he learned about this. And when he came back to this country, he brought that notation, the Gibbs notation, that we use for all of our vector calculus. Okay, so that's what he extracted from Hamilton's thing, and he threw the rest of it away. These are just vectors for him, not operators. For us, they're operators and vectors. And for Hamilton, too. Okay? Each Hamilton quaternion squares to -1. They are the hyper-complex, hyper-imaginary numbers. Just like an imaginary number. And that's what makes up the quaternion group, is 8 things, plus and minus each of these 4 quantities. Not something we're going to talk about today. Each Pauli squares to +1. Okay? Because he's got that extra I on there, so it doesn't square to -1 anymore. Hamilton wasn't interested in looking at something like that. If he had been, maybe his name would be in the quantum mechanics books. But he did everything that Pauli did and more without having to redefine a new thing. Okay, so now what we have to do is derive, and this is what we're really after. We want to solve this equation in a way we can visualize it. That's what we're going to really be getting, but also compute it more efficiently. So we're going to be solving the time evolution operator, which is the solution formally to that equation. And the spinor arithmetic will let us do this. And what I want to show is the analogy between the various parts of spinor analysis and just plain old complex variables. And this involves a form of what I call the crazy thing theorem. So let's go ahead and see what it is that our objective is. Our objective is to evaluate and, most importantly, visualize the solutions to this thing for, and remember I'm always putting down here, for constant A, B, C, and D, the four components that make up each of these main operators here. And this one is just something that drives the overall quantum phase. These are the things that make things happen. So we're going to be looking at some various kinds of funny notation for these exponentials. And we'll use lowercase Greek letters for descriptions of this thing as far as what's called a spinor space goes. So we're working at something that is behind the scenes of classical oscillation, in a sense. Okay, now the properties of squaring to 1, or minus 1 if you haven't bothered to stick the minus I or plus I onto a Pauli operator, is true not just for x, y, and z, or a, b, and c that we call them. It's true for any linear combination of them, provided the coefficients of the linear combination are that of a unit vector. So take any three numbers that square to 1, tack them on to sigma x, sigma y, and sigma z, just like that. And the notation we'll use for that thing is a dot product of some unit vector with a sigma vector. That is sigma sub a. That's the 8th component of sigma if the sigma x is the x component of this imaginary, of this weird sigma, and y the yth component, and z the zth component. This is any old component of the sigma that we're talking about here. And what does that component do? That is, if I take these two things and just plain square them as matrix products, then I'm squaring the matrix product of three things with three things, which makes 9 things. This is just putting all of this sigma a squared together as though it was a 3 by 3 matrix, but this is a sum. This thing plus this thing plus this thing plus this plus and plus. Okay? All right. Now you look at that thing, you reorder it so that you have sigma x squared here, sigma y squared here, sigma z squared right there, multiplied by a z squared, a y squared, a x squared. Okay? Then you have 6 other things corresponding to the off-diagonal products. All right, well, let's take a look at what those products are. One thing we notice is, for example, sigma z times sigma x comes out to be this thing, which is just I times sigma y, the thing that we call C, the green fellow, the one that does the currency in the current. Okay, and I'm using these colors to indicate that the green thing, this thing here, is the thing that makes things go. These two make things stop. They make standing waves. This is the only one that can get a moving wave going. But anyway, you'll notice that sigma z, sigma x is a negative of sigma x, sigma z. And this was the aha. Hamilton already knew that he had matrices that did this, but he didn't have it put together until he realized one day as he crossed this bridge in Dublin that, my gosh, I can do this wonderful thing in 3 dimensions. And I've got a 4th, I don't know what I'm going to do with that, but I've got the 3 taken care of now. And so that was a great big success for him. And what you're seeing here, you see, is that this cancels this cancels this, and this cancels that. So if x squared plus y squared plus z squared components add up to 1, then I get 1 for every one of the possible operators that you could make in that three-dimensional space. So sigma component anything, A for anything, squared is 1. That was the aha. Okay, that was a big aha, which led to this. We just use this stuff. I'm thinking about it, right? Pauli operators and things like that. Pauli doesn't give credit for this aha. Okay? And of course, Hamilton was getting a -1 because he didn't bother to put the little I onto this crazy thing. All right? But we're not done yet. We're not done. I mean, we canceled that out and this works and that's wonderful. But what about the algebra, the vector algebra that goes with this? You see? So that's what he rushed home to do. And it was either the next day or the next week or something. He came back and he wrote all of these relations, literally carved them into the oak posts of the bridge. And it sat there for years and years until about 1960 somebody said, hey, these are kind of getting a little weather worn. You could still read it. He carved it so deeply you could still read the equations. I squared equal -1. I times j equal k equal minus j times I. They're all there, these relations, you see. So they excised it from the bridge, and it's in a museum. There's a museum for Hamilton, and this was one of his main things that you can see in Dublin. I have not gone to Ireland. I haven't seen it, but there are lots of pictures you can get on the web. Okay? What we're going to be able to do here is dot in cross products with this stuff. Okay? So what's the product? We know what the product of sigma A with itself is. It's 1. But what about A and B? What happens when those two get multiplied? Okay? So now it's the same 9 terms here with minuses in various places depending on what the actually matrices do. And out comes the scalar product of A and B in 3 dimensions now, not 2 like the complex numbers did when we did the A star B back in chapter 10 of unit 1. Okay? And then here are all 3 cross products. We only got that last one, remember that? Pauli was complaining, hey, where are the other ones? There they are. That's Hamilton's discovery. Okay? Isn't that neat? Major crown jewel in mathematics here. Complex number is already a major crown jewel. All those good things that it does for us. Here it's doing it in 3 dimensions. When I do sigma dot A times sigma dot B, I'm going to get A dot B times the unit, and then I'm going to get the full A cross B multiplying the sigma here. Remember, sigma has that many components with an I. Okay? So that is a generalization in, this was 10th chapter, I'm sorry if I said that wrong. Equation 29, complex variable A star B, right? There's our scalar product, little 2 by 2, two-term thing, okay? And there's a z component of A cross B, okay? We looked at before, all right? So that's, to get, the history of this is useful for understanding it. And it gives you courage to go do crazy things, right? Looking for things that work and do good bookkeeping for you. Now, remember that there are lots of interesting complex functions. Well, there's some interesting spinor functions, and the exponential is one of them. So what he set to do, and he did this fairly quickly, was generalize these relations here. Okay? The Euler relations, the stuff that preceded by quite a few years, what he was doing. Okay? And this is considered a major development of mathematics, the idea that you take a crazy thing like the square root of -1 and be able to do all sorts of calculations that you would never have thought of doing otherwise. So, let's remember how that was proved. This is coming out of the 17th equation in chapter 10 of unit 1. Good old expansion of e to the minus I times italic phi here, which is not terribly good font to use when we're trying to video at high resolution. But if you zero in on that, you should probably be able to bring it up. In any case, you should already know that this breaks up into a cosine series and a minus I times a sine series, and that's what Hamilton already knew from Euler or the French mathematician de Moivre. I don't know the pronunciation for sure on that one. But the idea is that even powers of minus I are plus and minus 1, the odd powers are plus and minus I. So you have going through here a series of 4 things that you then recycle. So that's how you break the series up into even and odd parts. Hamilton replaces minus I with minus I times, you name the sigma. I'll take any component you want, or just eat one of the 3 individually. It's going to work. Okay, we're going to investigate those as they work solutions. And remember, our objective here is to solve this thing in a nice way. And that's what's being written here. But we haven't gotten there quite yet. We're almost there. Okay? So I've got to go through the series just like I do here. Minus I to the 0th power is plus 1. This thing presumably a plus, but I know I'm talking about a unit matrix. Okay? And then minus I to the 1st power is just minus I. So there's the thing that I'm going to be putting in an exponent up there. And then the square of that, oh, well, that's no problem. Okay, now I'm back to a real thing, but it's a real matrix, just like this is a real number with a negative sign. Then I've got plus I, okay, I got plus that weird, crazy thing. And then the 4th thing is just back to the unit operator, and then we start over here, okay? So I should be able to take this and plug in, and that's what he did. That's what Hamilton did. He just took this and plugged the crazy thing in, the whole thing. This is the crazy thing here, is minus I. That's the coefficient of the phi up there. Now he's going to plug it in. I used minus because it didn't signify that the crazy thing had a minus sign, and you should use it as such. Okay? So there's the crazy theorem. I used it last Friday, 1 week ago. Okay? E to the crazy thing times you name a parameter, and I will get, if the crazy thing squares to minus 1, I will get plus 1 times the cosine of that parameter, and then I'll get the crazy thing times the sine of that parameter. Remember that? Mm-hmm. Okay? So that's what this is. There's the crazy thing. Okay? And here's the crazy thing up here. Okay, it's this crazy thing, right? So all I have to do is break that crazy thing down into various things, write it all together there, and I've got a solution to this problem that I can write out by just cosine and sine of a parameter that I need to find when I'm doing this. But basically, there's the answer right there. I just have to take this crazy thing, multiply by a sine, and take a unit, multiply by a cosine, pull the overall phase thing out. That's the unit algebra. Remember, there's 4 things in the quaternion set. Okay? But when I'm done using that, and these are different notations for the crazy things components. Okay, this is a vector, it has 3 components. Okay, this little script phi here with an arrow on it indicates a vector with 3 components. This is a 3-dimensional space that's going to live in. This is just that omega vector that, times time. That's the angular velocity, the thing we'll call the crank of the Hamiltonian. And here are the actual values for a Hamiltonian. It has A, B, C, and D as its components. And that's all the components can have, remember, because it's got to be Hermitian. All right? Now, this can be generalized to do transformations in relativity, but that's taking it another level. Hamilton may have done that, but we don't know. So here's the old-fashioned crazy thing. It's just I or minus I, either one will work. And here it is with Pauli spinors or Hamilton quaternions in their proper places. Okay, so what's the geometry of the evolution or revolution operator? This thing, which is now written this way and can be expanded into a sine and cosine. And also, there's some mysterious factors that come up when we go out of the complex 2D space, which is called unitary two-group manifold, into the space we think we live in, which is a real three-dimensional spin vector space in this case. There's going to be a mysterious factor of 2 that keeps bothering you, keeps bugging you, keeps asking you what the hell's going on in nature. So this 2D spinor versus 3D vector rotation is something we really have to get familiar with. And then at the end of this, after we get all of this mysterious stuff worked out, we'll come back and just show you it's something you already know about if you've been studying the nuclear magnetic resonance Hamiltonian. Okay, they don't use this anymore because people are so afraid of nuclear things that they renamed the hospital nuclear magnetic resonance machine magnetic resonance imaging, MRI, right?
Oh, okay.
You'll never see nuclear. Bad. Okay. Yeah, you've got to do a lot of marketing in this country or you can't sell it anything no matter how good it is. So, here's the deal. Let's take a simple example. E to the minus this guy, sigma A. Okay? Well, that's just going to be sigma A times sine with the minus sign attached. Okay, you got to take the whole thing, leave off the parameter. The parameter goes in the sign and the coefficient goes in front of the sign. And then cosine of the other angle just times 1. Forget about whatever that sign was, right? So that's what his theorem, Euler's theorem taken to Hamilton's quaternions gives, all right? Well, let's just add it up. We don't get anything off diagonal because this is the asymmetric diagonal component, which he calls Z component. And all you're going to get is a diagonal cosine of phi minus I sine. Okay, that's what you're getting right here from the minus, right, and then the cosine. The cosine is still here, but with, let's see if this is right. I see, it looks like I've made a mistake here in the sign. That should be a minus I with a plus, okay? But in any case, I get e to the minus I phi and e to the plus I phi right here. Make a note. We've got to change that. That's been, I remember seeing that before and not changing it, so we've got to make a note. Okay, anyway, that's a Z rotation of a spinor. Pretty simple. Pretty simple. The other one that you will recognize, I'll go right to the C one. The C one is the next most simple one, and that's where we take the C operator, the thing with 0 minus I. It's got the minus sign up in the upper right-hand corner, just like a rotation matrix has a minus sign, S-I-N-E, right there, and then a positive sign down here. Here we have, a plus and minus sign. I've got a minus sign up here and a plus sign down there. So remember that the complex or imaginary component, the curly complex guy, has got that for his matrix. And then it's minus I times that and then the sign. So you put that thing together and look what you get. Just exactly a two-dimensional rotation by this phi, lowercase phi angle for the C operator. So if you've got any coefficient of this particular guy in your Hamiltonian here, okay, and we do, it's called uppercase C, that's from this thing, okay, then that's what you get if it's all by itself. If that's all you've got. All right, that's example 2. Now I'll let you do example B by yourself, it's a little different from this. It's got some imaginary stuff in the middle, so it's kind of weird. These two are pretty simple in terms of what you've already seen. But anyway, here's a general one. Let's just do the whole thing. This is e to the I, where I've got components phi that got A, B, and C, whatever. I've got a phi A, and I've got a phi B, and I got a phi C. Those are arbitrary numbers for a general case. Okay? Well, once again, it's unit times cosine, and then each one of the separate components contributes its matrix, its quaternion, its Pauli spinner. Bingo. That's all possible rotations that you can have in this U2 group, which is twice as big as the group that has the rotations in this room. You have taken care of a lot of arithmetic by doing this crazy thing, theorem. And you have solved this equation in a very graphical manner. Okay? So, old Euler's result generalizes to this, where this thing can have three components, red, yellow, and green. A, B, and C. X, Y, and Z if you cyclically permute it to Pauli's notation. Pauli-Jordan, by the way. Jordan's the mathematician behind that. Okay? So here's the two examples we already did. Now we're going to do something funny here. I want to rotate the actual sigmas. In other words, I want to apply one of these rotations, like this one, to a sigma operator, say sigma A. Okay, so I'm going to try to visualize in the three-dimensional space. I've got a sigma A operator, say right here. Now that's the Z, so I'm going to draw it like Pauli would want me to draw it. X and Y is sort of the plane, horizontal plane, and then there's a Z plane right here, which I call the A. That's the asymmetric diagonal operator that's getting worked on here. And I'm going to apply a rotation that's around the C axis, the Y axis. Okay? How he calls it Y. We call it curly, current, Coriolis, crap. I mean, you name it. If it begins with C, it probably applies to this operator. Anyway, I'm going to do the operation RAC on this thing. But this is an operator. I've got to do both the bras and the kits. So I need an R and an R inverse. This is the R, there's the R inverse. Real easy to just change the sign of the sign. And apply that to this. Okay, so when I do that, it looks pretty complicated at first. It's quadratic in the sines and cosines. But look, there's cosine 2 phi, there's sine of 2 phi. The cosine of 2 phi is multiplying a 1 minus 1 operator, so that's the sigma A. You knew it had to be a linear combination of A, B, and C. It just turns out to be only of A and B. Which is, if you looked at the geometry, pretty obvious. If I rotate around C, I'm not going to get a C in this thing, because A is perpendicular to C. It's just going to be a combination of A and B. Pauli's Z and X, and we're rotating around the C thing that he calls a Y. Okay? So we got Z and X in the milieu. Nothing's happening as far as getting a combination of C. Okay, so that's what I wanted you to see. A 3D rotation by twice the angle. It had to be twice because an operator needs to be hit by two of these spinner rotations. Now, note a little bit about notation here. Sometimes we like to write an operator's sigma whatever component, as the first component of sigma A, and the second component. These things right here are like unit. They're little hats on them, indicate unit, but in general we'd have an arrow on top of it indicate any magnitude for those. If those square up to 1, I put a little hat on that thing there to make a special generator whose square is 1. Okay, now we have to note that any 2 by 2 sigma matrix may be rotated by any of operator with any angle phi, not just one that squares up to 1 very nicely, acting twice, fore and aft, to give me an expression like this. Okay? It's a little bit of notation to indicate what's going on. So when we're talking about actually rotating in the spinor space, we're going to use lowercase things. But what we're doing here is we're performing a rotation in 3 dimensions, which is twice as big. And we have to get that factor of 2 squared away. Now, here, I'm writing this thing in a couple of different ways. I'm putting the A, B, and C components here, little hats on them, indicating that in general I would have a phi A, B, and C, and then multiplied by 1 over the square root of these things. So this thing came out to be a unit vector. So when you see a little unit vector here, it isn't just this. It's this divided by its length. If that's 1, then no big deal. But in general, that's what I'll be talking about when I put a little hat on the thing. I need a unit operator. Now later on we're going to write that operator in terms of velocity. It won't make any difference as long as you use cancel by that. This is an identity that we'll use considerably. So the punchline here is that this rotation of sigma B or this rotation of sigma A is going to give you linear combinations. First, cosine sine, that's the first column. Here's the second column, it's minus sine cosine. So what we've done is we've got a little 2 by 2 rotation of the Z and X axes, the A and the B axes going on here. This is a kind of weird geometry that we have to tackle, and the 2 phi is pretty mysterious. It gives me nightmares, actually. I'll try to explain why that is. But anyway, let's just review. We've got a Hamiltonian that we're going to be exponentiating because it's a solution to the oscillator two-level quantum system. We've got 4 components in here that are written what we call a dynamic phase that we usually take out because it's behind the scenes and invisible. And then the 3 components of the angular velocity, which is what this thing really corresponds to. And this is notation for spinor space, so we're using lowercase omega to describe it. Here's the omega vector and a sigma vector, and then there's the magnitude of the omega, and then there's the sigma with an omega component. And that's something that would square up to 1, and then the omega would take care of its absolute value. So here we are, asymmetric diagonal apart, bilaterally balanced, and circular complex. All right? Okay. Now, here's the notation that is preferable to use for thinking about this thing in a 3-dimensional space. This is the two-dimensional spinor space. Spin up is usually the x-axis. Spin down is the y-axis. That's kind of weird, isn't it? This is up, and that's down. That's the factor 2 coming in. Okay? But over in the real space, let's get real, things are very nice. They correspond to what we've got programmed in our amygdala, the concept of a 3-dimensional room. Okay? We've got that programmed. We don't have this programmed. You're going to have to think hard to get used to this one. But this one, well behaved. So I use uppercase letters because everything is going on twice as fast. in that place. Ever wondered why you get tired quicker? It's because you live in 3 dimensions where things go twice as fast. You gotta go live in spinner space, everything's half as fast. Okay? We'll see that. That factor of 2. All right? And we're going to write that using uppercase omega. Well, what have I done here? I'm going to take this 1/2 off of here and stick it on there. I'm going to take the B here and get a 1/2 over here, so I have to have 2B here. And the C here, again, I'm going to have a 1/2 over here, and I'm going to have 2C there. Okay? So this is uppercase omega, it's just twice lowercase omega. A factor of 2 again. Okay? You go slow in spinner space. You go fast in spin space. Okay? And this is a spin operator with a full 1/2 that we assign, a half quantum. And where does that come from? Well, it's pretty obvious. It comes from when the damn things are made. When a photon comes in with its spin 1 and doing all its polarization, presto changeo, out comes 2 guys with spin 1/2. And we're talking about one of them here. Okay? So these are the operators that have a mysterious 1/2. Okay? If that doesn't give you nightmares, you're not thinking. That should give every physicist nightmares. We've got to figure this out. What's going on? Okay? Take it, you know? We're not creationists. We're scientists. We should do better than that. At least we should worry about it. Okay? So, these guys are actually called Jordan's angular momentum operators with their extra 1/2. Okay? And what else? I think that's about it. I really don't have to do anything here, but I might as well change the notation. We could, play the games with 1/2 there, but it doesn't seem to, because we throw this away most of the time. Now, we do not throw this away in quantum information theory, because phase is absolutely essential for quantum information to mean anything. And that's precisely why it isn't making any progress right now, because phase is really elusive and really easily destroyed. And it's behind the scenes anyway, just thumbing its nose at you. Okay, so, be aware of that. Okay, so here's a notation for spinner space when it comes to actually using this Hamiltonian in the solution, the exponential solution. This is going to be broken up into something that's just an ordinary exponential multiplying something that's got the omega dot sigma, the component in the omega direction of that. So we've got a phi angle that we're going to rotate by, but I'm interested in the angular velocity of that. And the angular velocity is just given by these coefficients. In spinner space, a minus d over 2, b, c. But in vector space, it's given by not a minus d over 2, but a minus d. And 2 times b and 2 times c. Those are the big omegas. Okay? And the big theta. And this is little phi. And little omega. Okay? This is slow. Half as fast as this. Okay? And here's the same thing written out using the big notation that indicates fast stuff in our space, our spin space, our 3-dimensional space that we think we know. Boy, are we in for a shock. We don't know that. We just think we do. Because this is what's going on behind the scenes. This is what's driving it. Okay, so that's it. Now, this omega, okay, omega times t, this thing here, that's a crank vector. And this is a model right here of the spin that has various nice angles to describe it. You need a non-abelian coordinate system. It's basically a polar coordinate system for it. You also need a polar coordinate system for the operator. The operator is a crank that's going to be attached with suction cups in the model here to this thing at some arbitrary position, like that. And then the Hamiltonian is going to turn, turn, turn. And the spin vector that's inside that sphere is going to precess. That's NMR. But we're doing this for any 2x2 system, any two-dimensional, two-state system. Okay? And we're trying to keep track of phase. Where is the phase here, you see? Well, it might be disconnected with that. But this has got something, too, to show you. We have to make that connection. Okay? So we're almost there. And we're got about 20 minutes here to probably finish this to a reasonable state of completion. Okay. Now, let's talk about those mysterious factors again. Let's try to make them a little less mysterious. Here is spin up. Okay? Now, what does spin up mean? Well, spin up is going to literally mean spin up the z-axis, spin A for us. Okay? Now, when we apply an operator like this, we whip this one out. This was the operator around the y or c axis. Okay? We apply an operator to spin up. It's going to stop being up and start being a little downy, right? So as I turn this, it's only going to go cosine of beta over 2. Whereas the three-dimensional operator, which we're going to show ways to calculate very elegantly, before we're too far here, okay, is going to be rotated by a full angle, not half. Not beta over 2 is pi over 6 in this case, but pi over 3. So while this one's going to here, this one's going to go twice as far from here to here, 60 degrees. So I got 30, right? Okay? And we keep turning the crank to whichever, say pi over 4, okay? If we do pi over 4, this thing's going to go all the way to 90 degrees, right? Because this one went 45. Right? And finally, we're going to end up with spin down, right? Here, after we've gone 90 degrees here, we're going to be spin down. You see how going fast makes it kind of crazy? Okay? Let's keep going, okay? Here, I start here with spin down, okay, and keep going, right? This thing goes around, okay, around, around, okay, almost home. This thing's gone home, right? That thing's returned home. This one is not home. But it is spin up, but with a phase, with a pi phase. It's got a -1 right there. Doesn't have any minuses. Okay? So, I go like this. See the minus sign? I either have to go this way or I have to go this way to get back the smile, right? That's what this is telling you. If I'm an electron.
Yeah, that's what.
I've got a lot of electrons in me,
But
so
is there
I don't have to worry about this.
That's what the algebra tells us about it. Like when you rotate a spin half particle by 2 pi, it picks up a phase.
There it is.
Yeah, but is there a more rigorous reason that we can come up from the postulates of quantum mechanics as why a spin-half particle picks up a wave. The algebra tells us, but
It's a question I always used to ask professors. And I'll give you an answer like, yeah, it doesn't matter, or you'll never see it, or something like that, right? I'm going to try to show you why that is, but I'm not going to use electrons. I don't know what the hell an electron is. But I do have an analogy, and you should know what that analogy is. Photon spin. Polarization of electric field in laser beam. Okay? Ellipsometry, right? That's what we're doing here that's really powerful for our spectroscopy. So that's the thing we need to get with. Well, let's remember though, and I'm going to do this very quickly because I'm just reminding you that if you have a Hamiltonian that's the ABC type, ABCD, okay, type, we know how to handle it, right? And you will have such a Hamiltonian when you dot with B. B will be your crank vector. That's what this crank will be, is the direction of a magnetic field. And then that operator will act on the victim, which is this ball here that has a spin vector in it. I'm hoping I can make this thing out of clear plastic and have a big hunk of spin vector in there to scare people, okay? So those three components are just the three components of the magnetic field, Bz, Bx, and By, by Pauli's notation, right? So, to make a long story short, for this system where we really don't care about the overall phase, I just haven't added anything here that indicates that that's changing at all, and it's only differences that count in the MRI machine. So there's my omega, let her rip, right? Wherever you want to put that omega, then the thing's going to go around just like this machine does when I drive the crank, okay? The question is, how does the S define the state? Okay, we need a little bit more work on that. Now here's the way I can define the state using this machine. Now we're going to jump ahead and use a little bit of stuff from the chapter 6, I should say unit 6 of the thing, which I was trying to print today, and that's just when the Xerox machine decided it wasn't going to do anything. So you don't have that, but you do have it online. It's in nicer colors there. But the idea is that this set of Euler angles are polar coordinates, azimuthal coordinate for the spin vector that, imagine it's pointing right at you, right there, okay? So its azimuth is this dial at the very bottom. This thing right here is the Euler angle alpha dial, okay? And then beta equals 0, beta equal 98 degrees, beta equal pi. That's this angle right here, okay? And then this one's the gauge, gamma for gauge. That's the turning of the thing in its own frame, the electron spin's axis, okay? But we're going to use something besides electrons. We're going to use photons, and the vector in there also begins with S. It's called the Stokes vector. And that's the first time that this Jordan-type Hamilton-Pauli stuff really got used. 1863, 20 years after Hamilton discovered quaternions. John Stokes invented a way to describe polarization. It was so elegant nobody could learn it. But the basic idea here is that you can use the operators that we've already written to produce a state that has alpha, beta, gamma. And since we have a short time here, I'm going to speed this up. But you get the basic idea is that I'm going to do this just with the operator Z, that's the one we call A. I'll use Pauli notation. from now on. The operator y is sitting here, and we're going to use those two alone. Remember, those are the ones we worked out that were pretty simple. The y was a real operator that was off diagonal. This was just exponentials on diagonal. So that's the reason for using just the rotations z. These two rotations here, the z rotations, are used with this one in the middle. Okay? Now, if it's 3 by 3 space, you know what this does. If you've had your mechanics, this, you know, in the unit 6, you've probably seen this already. Here's a rotation by z, minus sign up where it should be. Okay. Here's another rotation around z that we're going to do after we do this one, and around y you have the minus down here. So you have to cycle x, y, and z through each other, not permitting singly. So these three matrices go together to make this thing. Okay? And what you see in the third column here are the lab frame polar coordinates, cosine azimuth, sine azimuth, and then polar coordinate. Beta rhymes with theta, sine theta, and then finally cosine theta, or beta. Okay? So that's the lab frame polar coordinates of the z-axis of the body. See the little z on the end there? It's kind of dented, scratched. But that's what is called, I call it the z-bar axis. So this is a coordinate transformation between the laboratory x, y, and I colored the z blue. It was colored back in the preceding slide correctly. And here are the body axes, not just the z bar, but also y bar and x bar, expressed in terms of the laboratory x, y, and z. Okay? And you can see this one's easy. That's just polar coordinates of the pointer. These are more complicated components here of the x bar and the y bar. You should expect, but this is a nice way to get them, and you're really sure about it once you've done this once or twice. Meanwhile, looking at the other way, this is the view from the body frame. Okay? These are the body frame polar coordinates of the laboratory z. The zenith is coming through see, I have this thing on the zenith of the laboratory right now, and these people that are riding on this globe here, you know, are using polar coordinates too. It's just they reverse alpha and gamma. And they also have a minus sign on all of their coordinates. So two minuses make a plus here. Cosine doesn't care about a minus. And here I have one sign, so I have a minus sign. Okay? These are little things that you should you know, notice when you do this, because if you don't get a minus here, you've done something wrong. Okay? So this is a picture of something I call rotational relativity. You really have to take this coordinate as seriously as the one that you're using to describe this whole business. The laboratory coordinates are presumably fixed here to the stars. They're not, because we're on the Earth and it's rotating, but at least they're fixed for a while and to the stars, a brief moment. And then there's this other thing that can be topsy-turvy. Okay, so bod view, body view, lab view. Okay, separate things. And the operators for one commute with the operators for the other. This is something that has not been treated correctly or fully by quantum mechanics, certainly in the introductory thing. So here's what we're going to do. We're going to use that sequence, first a gamma around z to set the phase, and that's what the other one was doing, you see. I'll go back there real quick. That's the first thing I do, is I set the gamma. So what I do is I apply the z operator right at the beginning. Now the thing would be lined up like this if I were setting everything equal to 0. Okay, so I apply the z, okay, operator, and then real quick I undo the screw here and bring it down to apply the Y operator, which then sets beta. I turn that to beta, whatever I want, upside down or just a little bit, whatever. And then I come back, and the last thing I do is use a Z rotation to set the azimuth. Okay? So now imagine there's a spin vector inside there, and we're doing this algebraically. Okay? First I apply that one. Okay? Then I apply that one, and then I apply that one. So here, first I set the phase, that's the gauge. Okay, nobody cares about that, so I could even cheat a little and not set the right number here, but let's suppose I did set the right number because I'm doing quantum information theory. And then I come around here to the y-axis and tip the arrow over. Okay? And then the last thing I do is swing azimuthally this spin vector. If I do alpha first, it's not going to do anything. I got to get it out here and then turn it, and then I end up with a general spin states at locations that you see there. So this is the general state of a two-state system parameterized by polar angles, alpha and beta. Notice the 2's in the denominator, even for the phase. Okay? Now, let's go ahead and see what the expectation values are for the A, that's the Z, the X, what we call B, and the Y, which we call C. So these are quantities of asymmetry, balance for B, and chirality for C that we're looking for our little polarization analog here. Okay? And here are the two amplitudes and the amplitude stars. Remember, we have to treat this thing as an expectation value that we're getting here of these operators, which have names that mean something, actually, for oscillators. Okay? And here's what you get. For this one, when you stick in the values for x1, p1, x2, and p2, which are the real and imaginary parts, respectively, of these components, you get a cosine squared minus sine squared of beta over 2, which is cosine beta. That's the third component for palette. It's our first. Our A is that. Okay? And then we go through and we look at the real and imaginary parts of these symmetric and anti-symmetric products. Those give you this and this, which boils down to that. They're the polar coordinates of that particular state. So now we have a really good idea of what's going on in a space we live in. We can take all of this complicated spinor stuff and just boil it down to a spin vector pointing in some direction with a twist, a gamma, a phase. Okay? Notice the phase gauge angle, gamma, is killed in this kind of description. This is a density matrix description where I have A star A everywhere. So I kill the overall phase. I can't see it in any of my expectation experiments. It's there. It's still there in U2 space. Okay? It's behind the scenes. So far behind, we don't see it directly. We have to have another spin system come up and beat with it, and then we get a difference from it. We'd never get the absolute value of it because we mess it up with the other system. So here's a typical polarization, elliptical polarization. And these angles have meaning on there. These angles, like phi, little phi, that's an alpha angle. Let's see if I've got that written over here. The phi it's a little bit complicated about how you take sums and differences of those things to actually get something. But the new angle right here is the aspect angle for the ellipse, and twice that is the polar elevation, not the polar angle, but the polar elevation. That's one of the hard things about this. And then this angle right here we can ascribe to something that's going on over there as well. So the various states, for example, this ellipse right here, there's something called a Faraday angle, which is the little phi. That's the one that's fairly easy to see. Twice that is the azimuth of the spin right here. Around the c-axis, not A and B, but around the c-axis. It really amazes me that Stokes was able to do calculations without having the structure that I've built here, because you really do need to have something to pin yourself to, or you're always making mistakes characterizing these. And these angles are being measured very precisely in some really neat experiments. So it's a technology that you should get used to. Now we've got just maybe a couple of minutes. I can show you some examples of rotations on the animation picture here. Let me first of all show you what would happen if I were to hit this. Let's see if I can get it going here. Yeah, there we go. Let me make this a little bit bigger. So it's easier to see. And let me turn it black. So it's also a little bit easier to see. And let's just do this one real slowly. This is an A operator. Okay, that means it cranks on the A axis. Right-hand rule makes the spin vector turn to circular polarization, which is a C state, and then it goes back to the other side where B, this is minus B, which is perpendicular, normal, to plus B in this space, but they're in line. And then there's a left-handed polarization right there. And then we're coming back to B. Now, this thing is going to come right there. It's down here. It's negative from where it was to start with. That's your pi. You can see this thing is pi out of phase after one rotation. But when it finishes this thing and comes back to B, it will be right there at the moment that it passes the equator. Okay, so there's your phase.
That's true. But do we understand why that happens, even in the case of photons? When you say, in this case, when you say, are you rotating?
Let me show you. Let's do this one. This is C. Okay. This is what's called focal pendulum precession. When you put your crank down here and you have a pendulum that can swing in. You know, in a museum they have the pendulums that cover an area as big as this room. Okay. So we're going to have one of those, but it's going to happen a lot faster with this. Let's go see that. I'll jump right to that one, then we'll come back to the B-type motion. So we'll go a slow roll here. Okay? See that thing? That's focal precession. You put yourself on a rotating Earth, and it's like having a magnetic field and a charged object. Or more precession is another name for it. You see the spin vector going from A around, okay? And it's just about to come home. Right now! And it was on the other side. Now, why is that? Let's stop this thing for just a moment here. Actually, that will, I think, stop it altogether. If I just click there, yeah. Anyway, think about what goes on when I apply and crank here, okay? And I'll start with what we started with, an A-type state that has X polarization, okay? Now I'm going to turn this thing, turn this thing, turn this thing, right? And when I get down here, it's going to be only rotating to here, 90 degrees, right? Mm-hmm. And then it's going to come back, and the red's going to be on this side. It's the topology of our three-dimensional space that forces it to happen here. It's a little harder to see it for this one, but it's the same thing. Now I forgot to bring a prop that would make this more spectacular, but here I'm going to demonstrate the same thing. When I take this object right here and point the little flapper at you, okay, what I would like to show you is it's possible without dislocating my wrist or my shoulder or wrecking my back or doing anything of injurious to my health. I am going to rotate this thing without letting it go and without spilling it. Suppose it would spill if a top is off, okay? Without spilling it, okay? I've now rotated about 90 degrees, right, in this room, okay? Now I've rotated 180, okay? And now, keeping it upright, I'm going to rotate it another full rotation. Okay? That's just the topology of this space we live in. The thing that's giving me nightmares. The spin-a-half space is behind us all.
So for spin-half, this sphere is nothing but the block sphere, right?
The block sphere is this thing.
The same thing for spin-half particle.
Yeah. With Rabi rotations going on, right? Get the names all right.
Can you repeat that one once again, Dr. Hunter? Like you have an arrow which is painted red to the right, at A.
Just follow it.
And then you just rotate that one, okay.
Yeah, just follow it. Just follow it around the track.
Okay.
Right? Like this one's doing for you, but you can see what it has to do.
Okay.
It's, you know, it only went to here, right? It's only going to be half done when it gets to there because it's going to be pointing that way, right? See it coming up there? This should be red, okay?
So it just has to do with the way it's rotated, right? This has nothing to do with any of the postulates of quantum mechanics, nothing of that kind. It has to do with...
But it's its whole body. Its whole, whatever it's made up this thing, is doing that. That's its pointer. Right? And same with this. Same, any rotation that I can do here, you see? Now, to help a little bit with this, let me, I'm going to skip this discussion here. You should look at this because this is where you mix this stuff all up and make avoided crossings, and this is what's behind the two hyperbolas that we sort of talked about. You see, I mean, this all comes together, this stuff, and makes you have nightmares. Let me back off here. Actually, I'll just escape and we'll play these things. I'm going to go get stuff that's in the group theory section of the thing. I'm going to pick out number 9 lecture from QTCA, which is this one right here. And what I want you, let's see if I can do it here, what I'd like you to see is just a, clear connection between these two. So let me bring this to 100%, and I might as well just play it, see what it does there. Yeah, so this is the thing we looked at that made a matrix based on Euler angles, okay? Suppose we just directly use the exponential operator, break it up into a, its sum, the thing that's up there in the exponent, in that sum, and work out that matrix. Now we did work this out just, roughly, okay? So this matrix here has to be equal to this matrix. I mean, here I got this thing into some configuration, here I got it into some configuration, or it's sitting there. There is a direct relationship between the alpha, beta, gamma, and the polar coordinates of the crank, which include its twist. You see, it's got a twist. That's your time axis up there. Here it's just an azimuth, but they're related. It's this relation right here between them. And the idea is that you're relating the phase x and p1 of this oscillator to the, and x2, p2. Both of those have to be equal no matter how I got this thing.